Hello everyone. Here's our integration review for exam 1, and we start with integrating fractions. And remember, to integrate fractions we have two new formulas. The integral of 1 over x with respect to x is the natural log of the absolute value of x plus our constant of integration, of course, and also the integral of what I like to think of as du over u turns out to be the natural log of the absolute value of u plus our constant. But remember, when looking at a fraction, the question we ask to determine if we're going to go for du over u or for u to the n is to ask if the denominator is raised to a power. If the denominator is not a power, that is, if it is just a function of x, we're going to try to fit the form of du over u. And if the denominator is a power, then we're going to modify it and try to fit the form of u to the n, which integrates to be u to the n plus 1 over n plus 1 plus our constant. Formally, we should say where n is not equal to negative 1. So, in the first set of problems, the first 4 examples actually, you see a bunch of fractions, so let's methodically go through these. First question, is the denominator a power? In number 1, letter B, nope, it's just a function of x. So we're going to try to fit du over u by choosing u to be the denominator, 1 minus x to the 4th. We then calculate our du. It's minus 4x cubed, formally the differential dx tagged along, and we modify, so we get negative 1/4 du is x cubed times dx. And then looking back at the integral, recall we were trying to fit the form of du over u. The denominator was chosen to be our u. Look at the leftovers, the numerator x cubed combined with the differential dx. Compare those to our du, and we see that they match, just modified by the negative 1/4. So replace those, the x cubed dx that is, by negative 1/4 du. And we've accounted for all factors of the integrand, so we can make the change of variables most efficiently, bring out the negative 1/4, and then fit the basic form. Upon change of variables, we have the integral of du over u. And so that integrates to be the natural log, so the negative 1/4 tags along. Du over u integrates to be the natural log of the absolute value of u, add our constant of integration at that point, and then back substitute. So negative 1/4 natural log absolute value, the u, 1 minus x to the 4th, and then carry along the constant of integration. Now, in letter C, again it's a fraction, and the denominator is not a power, and so we're going to try to fit the form for du over u again, and we're going to choose our u to be the denominator, 1 plus tangent of 7x. Okay, the differential du, derivative of 1 of course is 0, derivative of tangent, secant squared, same argument, 7x, don't forget, times 7, as well as the differential dx, routinely modified by the 7, so we have 1/7 du is secant squared of 7x times the differential dx. When we go back to our integral, we see that we were trying to fit the form of du over u again. We had chosen u to be the denominator. Leftover factors, secant squared 7x, combined with the differential dx, compared to our du, and we see they match, just modified by the 1/7. So replace those by 1/7 du, and we'll bring the 1/7 out in front, Change of variables gives us the basic formula for the integral of du over u again. And integrating, we get the natural log of the absolute value of u, add our constant of integration, and back substitute, so 1/7 natural log absolute value. U was 1 plus tangent 7x. Close up the absolute values, and plus our constant of integration. Okay, in letter M, there's some exponential functions. So what I'm trying to do is show you all the different types. You can have algebraics, trigs, exponentials. Again, it's a fraction, and again, the denominator is not a power. It's just a function of x. And so we're going to choose our u once again to be the denominator. 1 minus e to the 3x. Okay, when we calculate our du, just be careful. Derivative 1 is 0, that negative tags along. Make sure you put yourself in the differentiation mode here. The derivative of e to the 3x is e to the 3x times 3, and then the differential dx. And we modify by the negative and the 3, so negative 1/3 du is e to the 3x times the differential dx. Now we reflect on our integral. Again, we were trying to fit du over u by choosing u to be the denominator, the numerator e to the 3x combined with the differential dx. Compare them to our du, and no surprise, once again, they match. In this case, just modified by the negative 1/3. So we've accounted for all the factors, make the change of variables, most efficiently bring out the negative 1/3, and upon the change of variables, we have the basic formula for the integral of du over u again. So then we can integrate. Get negative 1/3, natural log, absolute value of u, add our constant, and then finally back substitute. So minus 1/3 natural log absolute value. U was 1 minus e to the 3x. Close up the absolute values and carry along our constant of integration. Right, now with all of those situations, knowing that we were going for du over u, it was possible to look at those and think that you can pretty much solve them by inspection. Well, not solve them by inspection, but at least you know that they were going to work. That is, because if we're looking for du over u, it's a situation where the derivative of the numerator, the derivative of the denominator is the numerator. And in all of those cases, it was kind of easy to verify, like the derivative of x to the 4th, 4x cubed. We'll modify by the negatives and everything and with regards to the particulars, but just to verify that they were going to work, like this one, derivative tangent, secant squared, and derivative of e to the 3x, e to the 3x times 3. But again, all the negatives, constant multiples, we'd worry about that. This one, not so easy to verify that it's going to work. So we have to trust in our integration strategy. And once again, we have two formulas for integrating fractions. They are either du over u if the denominator is not a power, or u to the n if the denominator is a power. And in this case, again, the denominator is not a power, so we're going to try to fit du over u by choosing our u to be the denominator. So we pick our u to be this string of terms, x to the 6th plus 2x cubed plus 6x plus 1. When we calculate our differential du, formally we do need to set of parentheses because our du is going to contain more than one term, and parentheses are necessary to write it correctly in differential form. And we differentiate, so we get 6x to the 5th plus 6x squared plus 6. Close the parentheses, because the derivative of 1, of course, is 0, and tag along the dx. Now, typically, the routine is to pick our u, calculate our du, and modify by a constant. But that constant, before we can divide out that constant, in every situation we've seen in these first three examples, we just had a single term multiplied by the constant, and we were able to divide it out. Here you have more than one term. So before you could divide out the constant has to be a common factor to each of the terms. And I think it's pretty clear here that our next move would be to consider that 6 is a common factor of each of these terms, so we'll factor out the 6. And we're left with x to the 5th plus x squared plus 1. And then times the differential dx. And now we can modify by the 6. So we get 1/6 du is the quantity x to the 5th plus x squared plus 1 times the differential dx. Okay, so now looking back at the integral, we see the denominator was chosen to be our u, and if you look at the terms in the numerator combined with the differential dx, they do identically match our du, just modified by the 1/6. So we could replace those by 1/6 du. We've accounted for all the factors of the integrand. We'll make the change of variables, bring out the 1/6, and upon change of variables, we have the integral of du over u. So no matter how complicated the integral is to begin with, you should always be able to bring it to a point where you fit a basic formula. And then there's 2 steps left. Integration, 1/6 tags long, du over u, integrates to the natural log of the absolute value of u, and then we back substitute. So 1/6 natural log absolute value. Make sure you put back the correct u, that was the x to the 6th plus 2x cubed plus 6x plus 1. Don't forget, close up the absolute values and carry along the constant. Alright, so those were nice examples of fitting the form of du over u. One special case that we talked about was when a natural log is involved in the integrand. If a natural log is involved in the integrand, what I told you was you want to pick it or the quantity associated with it to be your u, and hopefully the du will be there. And later on in the course, if the du is not there, we're going to have to make adjustments, but I guarantee for this first exam, you will get a question where the natural log will be a factor of the integrand and its du will be there. And knowing that that's true, we ask what's the derivative of the natural log of x, and we know that's 1 over x, and that's why there is this x in the denominator of this fraction to accommodate the differential of the natural log of x. So to make this clear, let's rewrite this. Instead of 1 over x times that quantity, let's isolate the 1 over x, knowing that that's going to help to satisfy the du. And then here I'm going to do this in one step. I'm going to rewrite the square root of 1 minus natural log of x. Excuse me. Because it is a power, we know the square root is the 1/2 power. So if it's a power, we also know it's going to fit the form of u to the n. So it's a 1/2 power in the denominator, so I'm going to shift it to the numerator as the quantity 1 minus natural log of x to the negative 1/2. And then I'm going to start a U-substitution by choosing u to be the quantity 1 minus the natural log of x. Not the power, because the power is accommodated in the formula for the integral of u to the n. And so, with respect to the integral, this is going to be u to the negative 1/2, and we hope our du will unfold to be the remaining factors. And our du is the derivative of 1 is 0, this negative tags along, derivative of the natural log of x, 1 over x, formally in differential form the dx as well. And now we modify by the negative, so we get negative du is 1 over x times the differential dx. And now going back to the integral, we've already set up u to the negative 1/2. Let's look at the leftover factors, 1 over x, differential dx, compare them to our du, and we see that they match, just modified by the negative. So replace those two factors by negative du, and we'll make the change of variables. But now we have minus the integral of u to the 1/2, negative 1/2 that is, times the differential du. So that's our basic formula in this case, u to the n, or u to the negative 1/2 in particular. And now integrating, the negative tags along, u to the negative 1/2 integrates to be u to the power 1 greater, which is positive 1/2, divided by that new exponent, add our constant of integration. And I'll just finish it off to the right here, dividing by a fraction, invert and multiply, so that becomes, carry along the negative 2, and put back our u, 1 minus natural log of x, now to the positive 1/2, and then plus our constant of integration. Okay, so moving on, we now have some situations where e is involved, and the formulas regarding e are the integral, basically just the integral of e to the x is e to the x, chain rule version, integral of e to the u with respect to u is e to the u. And then there was a special one, recall, the integral of e to the kx, what we called our linear argument rule. And the integral of e to the kx was 1 over k times e to the kx, and then plus a constant. So recall that we had a little bit of a hierarchy with respect to these different classes of functions. Remember, the 5 main classes of functions are described through this little acronym Y8. L stands for logs, I inverse trig, A for standard algebraic, T for your basic 6 trig functions, and E for exponential. And what we said was, if there is a product of an algebraic factor and an exponential factor, the exponentials dominate in our integration scheme or hierarchy. And so when we look at a problem like letter I, we focus on the fact that we have a product of algebraics and exponentials. Since the exponentials dominate, we're going to try to fit the form of e to the u. And we choose our u then to be the power on the base of e, 1 minus x to the 6th. The differential du then, this should be routine, minus 6x to the 5th times the differential dx as well. Modify, we get minus 1/6 du equals x to the 5th times the differential dx. And when we reflect back on the integral, we had already established we were trying to fit the form for e to the u. The leftover factors, x to the 5th, differential dx, compare them to our du, and they match, just modified by negative 1/6. So replace those factors by negative 1/6 du, and we can make the change of variables, bring out the negative 1/6, integral, now the basic formulas for e to the u with respect to u, and e to the u integrates to be e to the u, so negative 1/6 e to the u plus our constant, and finally back substitute, so negative 1/6 e to the u was 1 minus x to the 6th, and then plus or constant. Okay, and it doesn't matter how complicated the algebraic factors are. When we have a product again of exponentials and algebraics, exponentials dominate. So when we look at letter P, again, we should focus on E being the dominant factor and try to fit the form of e to the u by choosing u to be the power on the base of e, which is the square root of x. Now our hopes, of course, are that this 1 over the square root of x combined with the differential dx is what's going to make up our du. But here we have to exercise a little bit more care in calculating our du. When u is a polynomial, like example I, differentiation should be straightforward. Here, just be more careful, right? First rewrite it as x to the 1/2. Then our du is 1/2 x power 1 less negative 1/2, differential dx as well. Divide out the 1/2 for more efficiently. Think of multiplying by its reciprocal 2, and we get that 2 du is, at the same time, let's get rid of the negative exponent on x to the negative 1/2. Write it as 1 over x to the positive 1/2. And that actually should be enough to see that the leftovers do match, but if you want to show it literally, change the x to the 1/2 back to the square root of x. And now you can see that the leftovers in the integral, 1 over the square root of x combined with the differential dx, do make up exactly 2 du. So replace those factors by 2 du, and we'll make the change of variables, bring out the 2, and the basic formula once again is for e to the u with respect to u. And that integrates to be e to the u, so 2e to the u, add our constant at that point, and then finally back substitute, so 2e to the square root of x, and then plus our constant. Okay, so we have about 8 problems left to look at. I think I'm going to stop right there. We'll do a part 3 for this review. And so we'll come back and pick up where we left off.